name is Chrys Demetry, and I'm a professor in the Mechanical Engineering Department at WPI. The purpose of this video is to provide a window into a typical class period in my introductory material science course. I use a so-called flipped or inverted course design combined with team-based learning to foster a high level of engagement and learning both inside and outside of class. There are usually about 120 students in this course from all majors and class years. Both of those contextual factors definitely influence my course design decisions. At the beginning of the term, I form students into balanced teams of 5 using the CATME team formation software. I also use the CATME tool later in the course for peer feedback and evaluation. I do this because of the large body of research showing that peer learning and collaboration, properly structured for both individual accountability and team interaction, results in learning gains for all. These teams also become mini learning communities that give a large enrollment course a more personal feel. Each team is assigned to a particular location in the classroom, and they sit together during class. Here you can see how I accommodate 25 teams in the fixed seats of a lecture hall, leaving room for a TA and me to circulate during class. This diagram illustrates the daily rhythm of learning in the course. The essential idea is to enable students to begin learning foundational terminology and principles outside of class and hold them responsible for that. Class time can then be used to deepen their conceptual understanding, get questions answered, and practice applying knowledge in problem solving. Here's a typical learning cycle. The first thing students do is visit the Blackboard site for guidance on how to prepare for class. Each class period has a folder that lists the learning objectives and resources to prepare for class. Relevant textbook sections are listed, as well as some video microlectures that I prepared. There are usually 2 per class, sometimes 3, and each is 10 to 18 minutes in length. Students use whatever combination of the text and videos that they want to prepare for class. Skeletal slides are also posted for note-taking. Students take a comprehension check based on this material. This is a means of individual accountability, and it counts toward their course grade. Because of the large class size, these are usually a combination of multiple choice and short calculation questions that can be automatically graded by Blackboard. Sometimes I also ask an open-ended question, as you see here. The comprehension check is due 1 hour before class. I review their answers before class so that I know which questions, if any, need further explanation in class. During class, students do things. First, they take a team quiz. Then they work through some application problems. On the way into class, each team picks up a folder with the team quiz questions and application problems. Here's an example of the start of class.
Good afternoon. As you know, the intriguing question for today's class is how come when we deform many materials, including most metals and plastics, when we deform them, we actually make them stronger? That seems counterintuitive. It's really important for you to realize that when you deform a material, in other words, when you change its shape, you have the potential to change its properties, sometimes by quite a bit. So you'll actually get to feel that in a tactile, hands-on way in today's class with the plastic strip and paper clip. And you should also, by the end of class, have a better understanding of the structural origins of these strengthening effects. So I'll ask you to get started right away with the team quiz, which reviews some of the basics from the lectures.
The team quiz addresses the same foundational material as the individual comprehension check and usually consists of 3 or 4 questions. It's an opportunity for teams to help each other with the basics. These quizzes also count toward their grade And because peer evaluation is part of team-based learning, this adds another layer of accountability and incentive to prepare for class. The team quiz is deployed using the self-paced polling feature of Turning Point clickers. At the front podium, I check answers as they're coming in and decide how to proceed.
Your answers on those look pretty good, and instead of going through them now, I'm going to touch on each one as we do a more complicated problem on, from today's handout.
In this class, teams did uniformly well on the quiz, so I moved directly to a set of higher-level conceptual questions and application problems. If they had not done as well, I would spend time debriefing the quiz questions before moving on. In some cases, I'm able to ferret out misunderstandings using multiple choice clicker questions with good distractors that I know from experience will reveal common misconceptions and mistakes.
So I'd like you to put these two ideas together with question 5. So we start out with a rod with a circular diameter of 1 inch. We reduce it to 8/10 of an inch. Then we fully anneal it. So the fully is a cue that you can assume that the annealing treatment, sort of fully resets the material's properties to their original pre-worked condition. Then we further reduce the diameter to 6/10 of an inch. And then we would be able to look up the properties, say yield strength and ductility as a function of percent cold work. Some examples of that were shown in the lecture. So the question is, what percent cold work should you use in this situation? So you're going to need to decide which diameters to use, 1, 0.8, 0.6, and also properly calculate cross-sectional area. So give that a try individually, and then compare with people around you, and then I'll ask you to click in.
While students are working on these problems, I circulate around the room to answer questions and see how they're progressing. Depending on the complexity of the problem, I might give them anywhere from 2 to 4 minutes.
All right, let's see what we got. So about 2/3 C and the rest a smattering of the others. Someone who answered C, tell us how you figured which diameters you needed to use. JP.
I then reinforce the student's correct explanation and identify mistakes associated with the other responses.
So if we go from 0.8 to 0.6, which is a difference of 0.2 inches, and divide by the original 0.8, that's what I think this group was thinking. You forgot that for cross-sectional area, you can't simply use the diameter. You have to use the diameter squared or the radius squared. Either one will get you the right answer. So here you forgot to square the diameter. Here I think you went from 1 to 0.6 using the diameter rather than the diameter squared. And here I think you did square the diameter or the radius appropriately, but you went from 1 to 0.6. But you have to remember that that anneal resets, so the final step after the anneal is going to determine the properties. Any questions on that?
Not all objectives are conducive to clicker questions. Oftentimes I want students to explain their reasoning or generate an open-ended response. To increase the likelihood that students will really engage in these questions and stay on task, I call on teams to give a response rather than asking for volunteers.
Discuss it for a minute, and then I'm going to call on a team. Okay, someone on team 7, what's your explanation? What are the structural...
After class, I assign a homework problem. It's an integrative problem, but really at a similar level of difficulty as the in-class work. This completes the daily cycle of learning and practice. After a few years refining this course design, I now get consistently positive feedback from students about the value of the teamwork and the in-class problems to enhance their learning in the course. Students' self-reports of time spent on the course outside of class have also increased, which is good. And from the instructor's perspective, I really enjoy the dialogue and interaction with students during class. And the evidence of learning is tangible.